Assalamu alaikum. My name is Habibullah 21T79. Today we are discussing lab number 8 of digital signal processing. So moving towards lab number 8. The lab objective is number first is implementation and analysis of moving average filter, implementation and analysis of finite impulse response filter Fourier transform design method. Now moving toward task 1. In task 1 define a filter says define a filter. A filter in the context of digital signal processing refers to a system or algorithm that modified the characteristic of a digital signal. Filters are used to extract, enhance, and or suppress specific components of a signal based on their frequency, amplitude, or phase properties. Now, in second one types of filter. So there are many types of filters: low pass filter, high pass filter, baseband filter, band stop filter, band stop filter also called notch filter, and the last one is all pass filter. Now moving towards what are the time domain parameter of for a filter. So they there is also a few steps. The first one is step response. So the step response divided into two: good or bad. So a good step response indicates that the filter still quickly and smoothly to its final steady state value without significant overshoot or oscillation. This ensure that the filter accurately tracks change in the input signal and responds promptly to signal transients transition. Bad a poor step response may exhibit slow scaling time, excessive overshoot, undershoot, or oscillation. This can result in digital distortion and accuracies in tracking input changes and instability in the filter behavior. So the second one is overshoot. Overshoot is also good and bad. And then the third one is linear phase. Linear phase is also good and bad. So moving towards 4 point, what are the frequency domain parameter for a filter? So also have a few types. Roll off also have good and bad filter, and the ripple in pass band also good and bad, and the third one is poor stop band attenuation. This also is good and bad. So moving towards point 5, discuss the role of low pass filter for filter designing. The role of the low pass filter in filter designing includes: number first one is selecting desired frequencies while blocking higher frequencies. The second one is prevent aliasing and digital signal processing. Moving towards task 2, in task 2 says plot the signal in time and frequency domain along with its magnitude response. So we have x from 1 to 40 equal to 0. So the source code is defined the signal x is equal to 0, 1 to 40. So the plot the signal in the time domain, then compute the Fourier transform of the signal x is equal to f(t), and then compute the magnitude response, then plot the magnitude response in the frequency domain and plot the signal in the frequency domain. So this is the output of the given source code: the signal in time domain, magnitude response, and signal in frequency domain. So moving towards second source code. So x is equal to 41 to 120 equal to 1. Like previous, define the signal x is equal to 0, 1 to 120, then x is equal to x 41 to 120 equal to 1. So then plot the signal in the time domain, then compute the Fourier transform of the signal, then compute the magnitude response, then plot the magnitude response in the frequency domain, then plot the signal in frequency domain in FFT plot. Like previous, x is x 122 161 equal to 0. So the source code for this is like previous. So define the signal, then plot the signal in time domain, then plot the signal, then compute the Fourier transform of the signal, then compute the magnitude response, then plot the magnitude response of the frequency domain, then plot the signal in frequency domain. So the output like this is signal in time domain, magnitude response, and signal and frequency domain. Moving towards next, so x 121 to 161 equal to 0. So the source code for this x is equal to, for this x, define the signal x, then add noise to x. So x noise, so we add the noise with given x. So then plot the noisy signal in the time domain. Then compute the Fourier transform of the noisy signal. Then compute the magnitude response of the noisy signal. Then plot the magnitude response of the noisy signal in frequency domain. Then plot the noisy signal in frequency domain. So we get an output like this: noisy signal in time domain, then magnitude response of noisy signal, then noisy signal in frequency domain. Moving towards next task. So x noise equal to x plus 0.5 uh, radian size x. So the source code for this x is that define the signal. First we define the signal, then add the noise to x, then define the moving average filter coefficient, then apply the moving average filter to the x noise, then plot the filter signal in the time domain. Compute the Fourier transform of this filter signal, and compute the magnitude response of the filter signal, then plot the magnitude response of the filter signal in frequency domain, and plot the filter signal in the frequency domain. So this is the output: filter signal in time domain, magnitude response of the filter signal in frequency domain. Now moving towards apply three taps symmetrically around moving average filter on a signal X noise and absorb the time and frequency domain parameter. So the source code for this is defined. First we define the signal, then add the noise to the X signal, then define moving average filter coefficient, and apply moving average filter to a noise signal, then plot the filter signal in the time domain, then compute the Fourier transform of the filter signal, and compute the magnitude response of the filter signal. Then plot the magnitude response of the filter signal in the frequency domain. Then plot the filtered signal in frequency domain. So this is the output: filter signal in time domain, magnitude response of the filter signal in frequency domain. Now apply 11 taps symmetrically around average filter on a signal X noise and observe the time and frequency domain parameter. This is also like previous task. So first we define a signal, then add noise to the X, then define the moving average filter coefficient, then apply the moving average filter to the X noise, then plot the filter signal in the time domain, then compute the Fourier transform of the filter signal, and compute the magnitude response of the filter signal, and plot the magnitude response in the filter signal and frequency domain, then plot the filter signal and frequency domain. So filter signal in time domain, magnitude response of the filter signal, and filter signal in frequency domain. These three are the output of the given source code. Then says that apply 25 taps symmetrically around moving average filter on X on signal X noise and observe the time and frequency domain parameter. This is also like previous code. So the source code is time to define the time, define the signal, then add noise to X, then define the moving average filter coefficient, and apply the moving average filter to a noise, then plot the filter signal in the time domain, and compute the Fourier transform of the filter signal, and compute the magnitude response of the filter signal, and plot the magnitude response of the filter signal in frequency domain, and plot the filtered in the frequency domain. So as a result, we get an output like this: filter signal in time domain, magnitude response of the filter signal, and the filter signal in frequency domain.